Hey guys, what's going on? This is meteorologist Chris Lasakis for Eyes to the Sky Environmental Services. I want to take some time today to actually go over with you a topic on Isallobaric forcing, something I've been meaning to discuss for a while. What is it? Well, basically, an Isalobar is a line connecting points of equal pressure change, also known as pressure tendency. That's another way that you'll hear that stated. And an Isalobar is both a pressure rise or a pressure fall, depending on the tendency. Which way that pressure tendency is going. Is the pressure rising or falling? So it encompasses both terminologies. Isallobaric flow is the ageostrophic component of the pressure gradient force. This is getting a little scientific, but of course that's okay here. But that's, generally speaking, that's what it's considered, the ageostrophic component of the PGF. Generally speaking, lows or highs move toward the greatest pressure falls or rises. This is a way you'll see the terminology in a lot of literature right here. The lows is associated with falls, right? And the highs is associated with rises. That's how you can look at that. Isallobaric flow is one of the 5 terms within the ageostrophic wind equation. You'll see this in a lot of meteorology texts. Or if you go to school, obviously you'll see it in lecture for meteorology. Down here we'll see that a catalobar is the term for a pressure fall portion of the Isallobaric analyses. And an Isallobaric is the term for pressure rise portion of Isallobaric analysis. So you'll see these two thrown around loosely every now and then if you read an area forecast discussion written by a National Weather Service forecaster. Every now and then the Storm Prediction Center also will throw that out there when discussing pressure tendency. But just know that, know the differences between the two. Isallobaric analysis allows forecasters to potentially anticipate where severe storms will develop. And it helps to identify fields of enhanced storm relative helicity. This is actually something I'm still looking into, still researching this. But this right here does have a lot of potential. You'll oftentimes find that the greatest storm relative helicity fields on a map, on a planned position indicator map, will be co-located with the greatest Isallobaric forcing or Isallobaric flow. This isn't always the case, but especially in the greater baroclinic or frontal environments, you'll find that that's the case. So, going down the list now, although often a good technique, it is crucial that forecasters understand that Isallobaric analysis cannot be used for every storm environment. Sometimes in a lightly baroclinic or more barotropic environment where there's not real strong fronts, where you don't have strong height falls aloft, don't have a strong low-level jet as a result, many times you won't have that real tight pressure tendency or that Isallobaric response at the surface. And so in that case you'll want to use more co-location of greatest instability with warm air advection tendency and stuff like that to help you better forecast. Locations of moist dry couplets aloft in the mid-levels associated with the EML. There's many other things that you can use in lieu of or in place of for forecasting severe storms when the Isallobaric method can't be used for Isallobaric analysis. So again, if it does not exist in a severe storm environment, then attention is due to the specific threat area suggested. So in other words, I'm going to show you some examples in a moment. When it does exist in an environment that you've kind of outlined for severe weather, really pay attention to that. Some additional material, Uccellini and Johnson from 1979. A quote from them was, "The pressure tendency at an altitude of z, or height z, is due to the net mass change of the air above that altitude." So as height changes, the pressure tendency is also going to have to flux or to adjust to that change in mass response above it, is basically, in layman terms, what that's indicating. Togstad from 1994. This is a very difficult to find publication. It's one I'm still searching for. I have not been able to find it. I really want to read through it because apparently it's really good. Bill Togstad was a National Weather Service, a veteran National Weather Service lead forecaster at both the Minneapolis and Chanhassen offices back in, I think, for 25, 30 years, from like the 70s through about the late 90s, early O's. And he was a absolutely fantastic storm researcher as well. Had a lot of good publications. But if you can find this one, good luck. Let me know if you do, though, because I'm in search of it right now. I'm looking out for it. John Sturdivant in 95 with his book, The Severe Local Storm Forecasting Primer. Had some good quotes and a good page worth of discussion about Isallobaric analysis. One of his was Isallobaric analysis allows the forecaster to anticipate corridors of rapidly moving tornadic storms a couple hours beforehand. That's a good one. And then going down to the very bottom, this is from Jack Hales from the Storm Prediction Center, one of his publications in 96. Just quoting that many severe weather outbreaks are preceded by 1 to 2 hours of strong pressure falls, such as the Tulsa tornado of 1993. So he cites a specific example there that he observed. So let's jump right into some examples. I know this is generally what we all are waiting to see. It's the good stuff. This is from April 27th, 2011 at 4 p.m. Central Daylight Time. As many of you know, the tornado outbreak was ongoing at 4 p.m. from roughly Huntsville down to just north of Montgomery, right in this corridor, right in through here. And interestingly, as you can see, this is the area of greatest Isallobaric response. One of the things that you're going to want to look for when I say Isallobaric flow or Isallobaric response, look for the region where these isobars, iso meaning areas, lines, points of equal pressure, lines connecting regions of equal pressure. So you can see the 1000 millibar isobar, the 1000 millibar isobar right in through here from central Alabama north is kind of the northern extent of the greatest Isallobaric response. See how these isobars are packed about evenly through this region here. And then as you get north of about Coleman or west of Scottsboro, they become a little more disjointed or unevenly spread. And so the greatest Isallobaric response obviously was down in through this region in central Alabama into northeast Alabama, and that actually is where the bulk, the core of the tornado outbreak was occurring at this time. And as we know, we had that lone supercell that tracked from just southwest of Hackleburg, Alabama to northeast of Fayetteville, Tennessee between 2 and 5 p.m. that would have been along that boundary, that theta E low-level baroclinic boundary that was laid down earlier in the day. But that would be the exception. Other than that, you could have used this method very well to distinguish the core of the tornado outbreak. And also notice, if you will, not only the spacing of the isobars, but the orientation of the surface winds, the 10-meter winds, which are considered surface winds in meteorology. Notice the orientation of those to the actual isobars. So that's what we have going on here. Like if you take, for example, an area in Florida, like here, they're more parallel to the isobars, the wind barbs are. Here you have them almost at 90 degrees, but still the packing of these isobars is not the same down in through here. So you know there's something special or something serious going on in through this region and through the area highlighted in red. And we will go on and use some more examples to help you understand. This is from March 2nd, 2012, 9 a.m. Central Standard Time. Many of you probably remember this event. It was a pair of EF3 tornadoes in the morning, followed by a lull in the early afternoon, and then more tornadoes, weaker tornadoes, throughout the midday hours into the early evening. You can see here there is a nice Isallobaric response, very tightly packed isobars throughout much of the Ohio Valley and into the lower Mississippi Valley through the Tennessee valleys. But there's something very subtle that I want you to try to notice here. This takes practice, but this is one of the reasons why I'm doing this video, is to help you with the subtleties. Notice how, specifically how, of course, Huntsville is just to the east of this red dot. The red dot is approximately the tornado location of tornado genesis near Limestone County. But notice how the isobars kind of flatten out as you head east to west. If I can get my cursor to respond here. So you have mostly a southwest-northeast orientation of the isobar pattern in through Mississippi, in through western Tennessee. But as you get into southern middle Tennessee and northern Alabama, notice how they kind of turn more easterly here. You see it a lot in this isobar in northern Alabama, and a little bit in this one in southern Tennessee. But you have southwest, southwest, northeast, and then all of a sudden it kind of flattens out right in through here and turns more east-northeast. Well, that's indicating probably a shortwave trough aloft that was very difficult to pick up using probably both water vapor imagery and mid-level SPC mesoanalysis data. With this being at the 9 a.m. hour, it was after the morning balloon soundings were put out, about 3 hours after that, 3 to 4 hours, and so it would have been hard to resolve in the radiosonde network. It's possible that it could have been detected further back southwest, but anyway, I don't want to digress too far there. The point is that using surface analyses, these little subtleties like this, when you have this discontinuity or this irregular pattern, and then notice because it turns more easterly here, this isobar, this one's slightly as well, but again this one's favored most, it allows the surface winds to be at a greater angle to that area. And so what that's showing us is there's a greater Isallobaric response, or a greater ageostrophic wind component, specifically right in through here. And that's exactly where that severe thunderstorm producing that tornado was ongoing at this time. It just began to develop. So that's interesting. Look for those subtleties. We're going to use another example. This is from Super Tuesday, February 5th, 2008. This mesoanalysis chart was taken from the SPC Mesoanalysis Archive. You can Google that and obtain a link for it if you'd like to do more research. This was from 7 p.m. on Super Tuesday, 08. And you may look at this, and as I first did, and think, wow, you know, this is kind of a messy pattern. There's a lot going on here, and you're right. You know, you have this strong area of surface low pressure turning counterclockwise, centered near the boot heel of Missouri. But it's kind of elongated pressure trough. But the Isallobaric response, as you can see, is mostly going to be on the eastern side of that. Obviously within the warm sector, right? That's where we want to look for tornadic potential. So the greatest instability would be located, you know, somewhere right in through here at this hour. And the packing of the isobars is strong all the way in through here and extending down into central Mississippi as well. So from the Ohio Valley, south-southwest, into the middle Mississippi or southern Mississippi Valley. But there's a little bit of difference. If you look real close, right in through southwestern Tennessee, there's a maximum in how close these isobars are packed. There's an area of really concentrated isobars. It's subtle, but if you look, it's located right in through here. And the wind barbs, the 10-meter surface winds, are crossing that at nearly a perfect 90-degree angle right in through here. And so that's telling you that there's a strong ageostrophic component there, and the Isallobaric response, or the pressure fall component, is very strong in through this region. And the ageostrophic component obviously is comparing the surface wind flow and to those isobars, or the angle at which the surface wind barbs are crossing the isobars. And that again is peaked right at about where the red dot is located. And there's one more thing, if you'll look closely, you'll notice almost like a little bowing pattern right here, and as you go from this straight line almost like an inflection right in through here, and then the isobars turn more southwesterly or more westerly than they were up in here when they were more southwest. So right in there, you almost have a little kink where the dot is. And there was a violent tornado ongoing at this time at the red dot location in Savannah, Tennessee, or Hardin County, Tennessee. It was F4. It was one of a handful of F4 tornadoes that developed during this event and moved from northern central Mississippi on into actually southern Kentucky as the event progressed through the evening hours of the 5th and actually into the early morning hours of February 6th, when we had a pair of violent tornadoes that sadly resulted in some people perishing here in northern Alabama. But again, that's just another example. I want to move on now to an example. This is April 7th, 2006. This was actually a high-risk event. February 5th and 6th, February 5th, 2008, the previous one, Super Tuesday, that was a high risk as well. But this was a high-risk event that did not pan out very well. This is actually one of the lesser high-risk events that I know of personally. It was a 60% hatched tornado threat in through southwest Tennessee and northwest Alabama, northeast Mississippi, say from about Tupelo, Corinth, up to about Decatur County, Tennessee, and or about Jackson, and south to about Franklin County, Alabama. So this region right in through here was, and that was the first time that a day 2 high risk had ever been issued. But anyway, all weather history aside, looking at the surface map here, you see first off that there's not really a strong Isallobaric response, is there, in northern Alabama, especially where that 60% tornado risk was, which was right in through here, kind of in the western half of this red circle. And so that should have alerted, some forecasters to say, hey, there's something's not right here in the environment. Unless we had had extreme instability to help, stretch or converge those updrafts and those mesocyclones, there just wasn't the low-level kinematics or wind flow that we needed to support violent tornadoes on this day. And this should have, been a sign to mesoscale forecasters, hey, look, something's not right. Something's not coming together like we had thought, especially also since, and they're related, but since the agiostrophic component of the wind flow was not oriented at a sharp angle to these isobars here in northern Alabama. You can see they're kind of parallel, or just kind of random, almost. Of course, we were probably developing convection at this point, so we had wind gusts in different directions, kind of resulting in this random wind pattern. But nonetheless, there should have been more of an agiostrophic component, A, right, and B, we should have had tighter Isallobaric response or tighter isobars in northern Alabama. And you can see that's all down here in central Alabama and southern Alabama and Mississippi, way further south of the threat area. So I think there were a handful of EF1 tornadoes associated with the high risk that day in the 60% area, but certainly nothing worth a 60% day 2 high risk highlighting violent tornadoes. But that's okay. We all make mistakes, and the weather field is an ongoing thing. Research, we all live and learn, and it's difficult to get it right 100% of the time. We all know that. So this is an interesting case study, and I certainly learned a lot from this. Because back in the day, this was 11 years ago, I was even thinking that it was going to be an extreme event, just because I hadn't really sat down. And hindsight's always 20/20. But I got a lot out of this event. And so we'll move on now to June 29th, 2017. This is just a few days ago. Today is actually July 1st, 2017. And there was a tornado in northeastern Nebraska on this evening. And I use this example. Of course, the imagery here comes from Twister data. This isn't SPC mesoanalysis data. This comes from the good folks over at twisterdata.com, who produce some wonderful maps. Definitely want to give them props for this. So, yeah, you can see the surface low You have cyclonic flow right in through here, northeast Nebraska. And the tornado occurred right in here in the very northeastern portions of the state. You can see that the Isallobaric response is not very strong. You don't have closely spaced isobars here. Of course, your isobars on this chart are every 4 millibars. The SPC mesoanalysis features them every 2. So they wouldn't be as closely spaced on this map to begin with. That's just something to keep in mind. But nonetheless, they're not anywhere near even as a ratio as close as you would expect them to be for a tornadic environment. But this event featured extreme instability, a -10 lifted index with like 3,500 K, joules per kilogram of K, between 3 and 3,500 joules. So 3,000 and 3,500. So that allowed for very strong stretching of the updrafts, and that kind of, made up for the lack of low-level kinematics or wind flow support that Isallobaric flow would suggest. So very weak here, but it was made up for by the instability, as you can see. So as I mentioned before, not every case is going to feature strong Isallobaric flow. Sometimes even very, very little, if any, as was the case in this example. Another example this is one of my favorites, from January 22nd, 2017. Me and a group of friends actually chased this storm system down in southwest Georgia. We went down there for the weekend and barely missed the Albany, Georgia EF3. We were down here near Cairo, Georgia, and as the low-level jet was kicking in, we were just in awe of how strong the environment was becoming. And one thing I personally failed to do was check the Isallobaric analysis, or perform one. And if we had, we would have seen that the greatest Isallobaric response was right in through here, through southwest Georgia, which is where we were, but that the agiostrophic component, or the orientation of the surface wind barb to the isobars, was most perpendicular right in through here, or just to the east of Albany. Of course, the tornado time, I believe, was just prior to this. So this would have guided us right up into that area just about perfectly. Again, not every example works out this well, but it certainly would have done us a world of good to check and perform a Isallobaric analysis before settling on a target location. So that was a good lesson learned by me, and certainly will help in the future. So just some references now in closing. Hope you all have gotten a lot out of this. This has been one of the discussions I've been meaning to do for a while. Again, as far as looking for specific publications, this internal publication, I believe, is probably the best one. It was done by Bill Togstad from the National Weather Service in Chanhassen, Minnesota in '94. It was titled "The Isallobaric Wind as a Forcing Function on Fields of Helicity." That's actually an idea that my advisor and I, Dr. Kevin Upp, have talked about. I've actually looked into it a bit for my thesis, and it's something that's highly beneficial, but I can't find the publication. I believe it's probably an internal one. I plan on contacting the National Weather Service soon for that. Anyway, I hope you all have gotten a lot out of this, and have a great day.